to use set theory laws, intersection B, union A, union B, complement is equivalent to B. Right? So on that particular instance, we have got A intersection B, union A, union B, complement is equivalent to B. So we are going to pick the left-hand side by using the left-hand side. So we are going to expand A union B, union, then we introduce the De Morgan law there. Is A complement intersection B complement should be equal to B. So it's A union B union A complement intersection B is equivalent to B.
Sorry, Steve.
So
can you pick it up that you said a union?
Okay. On this part, I need. Right. Let's deepen upon what now.
Yes, sir. Yes.
All right, that's fine. I think I just said a writing error there. Thank you for that. So we can now what we can do, because we have things that we can see from that proof, okay, which we can make use of, because by the commutative law, I can change this one to be intersection A if I want, or I can leave it like that so that I move this one. I can leave it like that so that I move this one. So I can have A intersection B union, then I can change this one. B intersection A complement is equivalent to B. One noise, side noise. Mute yourself. So I still can play around with this one. However, B intersection A, just using the commutative law, union B intersection A complement is equivalent to B. Then from there, I see that B intersection is common. I can revert back to the distributive law by factoring out B intersection. So B intersection, this is the universal set. Everything in A, union everything that is outside A is the universal set. And the B intersection, the universal set is B. So can go to that stage. So that's how you solve. So coming up with the diagrams, like event diagrams, to prove an instruction that was told to use set theory laws, we will actually make your problem incorrect. And so that's how you solve that one. We can have another one, then we'll move on to the next item, otherwise we'll not be able to finish. A intersection A union B is equivalent to A. So there are things that you can that you need to do on that particular instance, so that you I see that if I'm going to use the left hand side, I can see that if I'm going to use the left hand side, it means that I have to introduce something that eliminates B. Okay, so what I can do is I can introduce an intelligent empty set on that particular instance, so that that empty set at some point maybe it will be able to eliminate B, but I have to introduce it intelligently so that it does not affect or it does not change the meaning of the original problem. So I can use on this part, I can say A union an empty set. I think this is still A. Intersection, this A. A union B. This one should be equivalent to A. What I've done is just I have introduced an intelligent empty set, but it does not change the meaning of the problem, because A union the empty set is still A, which is this A. So I can see that A union by the distributive law, I can factor out A union. Then I have empty set intersection B should be equivalent to A. Then I can know that A union the intersection of B and the empty set is the empty set, which is equivalent to A there. We can move on to the next item. We can move on to the next item. So we can have another one. A set difference B is equal or equivalent. Let me use a fresh page. Quite low. Right. A set difference B, set difference C is equal to A set difference C set difference B. So we can use the left hand side to go to the right hand side. I'm using the left hand side, which is A set difference B set difference C. So I can remember when we started, we have got three ways of representing the set difference. We have got three ways of representing the set difference, right? We can have so the set difference, you can still represent this part. This part we say is the same as A intersection B complement set difference C. Then this can still have, because this, if we treat it as one, it's like one letter set difference C, like what we have inside there. So I can move on to say A intersection B complement in brackets intersection C intersection C complement. And by the associative law, I still can now shift brackets based on those things. because it's A intersection B complement intersection C complement. I can move brackets because I know that I'm dealing only with the intersection. Then I can still move brackets so that it goes to where I want it to go. So I can actually have A intersection C complement, intersection B complement, but this is A set difference C, intersection B complement, but also A set difference B, which is what I wanted to do. So on that note, we can stop on sets. You are going to encounter issues to do with set difference, not a set difference per se, but set theory laws, right? Set theory laws. Then from there, you are going to also deal with problems that involve three sets, come up with a Venn diagram, then you solve the rest of the problems. Then you solve the rest of the problems. I'll try to quickly move on to relations. Relations. There are a few things that you need to worry about on relations. There are things that you need to worry about on relations that should be with you as you try to look at problems. Okay. So a relation on a set X, for example, or let's have it on a set X, is a subset of the Cartesian product X on X. Or if it is a relation from set X to Y, for example, is still a subset of the Cartesian product X cross Y, or if you want A cross B. Things to note is that a relation is a subset of a Cartesian product. Either if I've got one set, it's that set on itself, or if I have got two different sets, it's a Cartesian product of those two sets. But this is a subset of the Cartesian product. When we started, we defined a Cartesian product as a set of ordered pairs, right? If we have got two sets A and B, then we said that the Cartesian product is a set of ordered pairs that are coming from A to B. The word ordered means the way in which you represent the sets is important. The way in which you represent the sets is important. They follow a particular order. So this is what we want to look at on relations, right? So if I have got a set X, for example. So relations, with the way you come up with your relations, you are supposed to satisfy particular conditions that are provided in the person, right? So if I have got set X, for example, with the elements 1, 2, 3, and 5, for example, then I've got another set Y with the sets 1, 2 elements, 1, 2, and 2, 7. Then I'm saying that X, Y is an element of the relation R if and only if X divides Y. If and only if X divides Y, then I'm told to find R, the relation. So I've got two sets, X and Y. X has elements is elements 2, 3, 5, and Y has elements 1, 2 until 7, right? And XY is an element of R in that order. X and Y is an element of R if and only if X divides Y. Then I'm supposed to find R. So I'm going to come up with a relation. And the elements of this relation, which are formed by satisfying the condition that X divides Y, are based on the fact that the elements should be a subset of the Cartesian product of X cross Y. What it means is the elements that we say these are the elements of R, for example, when we perform a Cartesian product XY, we should find those same elements being in that Cartesian product. But here we are just picking R as a subset. So we are looking at X divides Y. So I can come and put 2, 2. I can come and put 2, 4. I can come and put 2, 6. I can go to 3, 3. I can go to 3, 6. I can stop at 5, 5. So these are the elements of R based on the condition that X divides Y. So if we are going to perform a Cartesian product of XY, we still find these elements of R being there because R is a subset of the Cartesian product X cross Y, which is what we want. We can still have another one where we have X having elements 1, 2, 3. And we are looking, and we are told that R is a relation. R is a relation on X, set X, and X, comma Y is an element of R if and only if X is smaller than or equal to Y. Then we are told to find R. Then we are told to find R. So in that particular instance, it's simple. We are going to just come up with R, which is again a subset of the Cartesian product X on itself, X cross X. Then provided X is smaller than or equal to Y. Then we have got 1, 1. Then we have got 1, 2. Then we have got 1, 3. Then we have got 2, 2. Then we have got 2, 3. Then we have got 3, 3. So these are the elements of R, which we refer to as the Cartesian, the subset of the Cartesian product. So we are coming up with R based on the fact that X is smaller than or equal to Y. Then now you can move on. So there are instances whereby I can move on to represent this output R in the form of a graph or a directed graph. If I want to represent that relation in a form of a graph, I can have the elements from the set, 1 there, 2 there, 3 there. Then we have got an arrow from 1 to 2. We've got an arrow from 2 to 3. Then we still have got an arrow from 1 to 3. Then at some point we are looping. We are also looping. Then we are also looping. So I can still represent the output of the relation as a directed graph based on the previous output that we had. We want to define what we call an equivalence relation. An equivalence relation. So when you are told to verify or when you are told to test that a particular a particular relation is an equivalence relation, what you are being asked to verify are three things. You are being asked to verify three things. You are being asked to verify if that relation is reflexive, if that relation is transitive, if that relation is symmetric. In some text, you will find they also talk of anti-symmetric, but we are only worried about three conditions for purposes of this course: reflexive, symmetric, and transitive. These are the three that we are really worried about. For you to be able to verify those three, you should have a proper definition of each, because these are important things when you are dealing with relations. So let R be the relation on set X. Let R be the relation on set X. We say that R is a reflexive if we say that R is reflexive if for OX element of R, element of X rather, XX is an element of R, right? So reflexiveness, here we are saying that if R is a relation on a set X, we say that R is a reflexive if for OX element of X, the set, then these elements are elements of R. So we are looking for similar XX, 1, 1, 2, 2, 3, 3, as we go on like that. If that one is an element of R, provided they belong to the set X, then we can talk of reflexiveness. Then R is symmetric. R is symmetric if for all X, Y, elements of X, if XY is an element of R, then YX is also an element of R. So what it means is that if I have got 1, 2 being an element of R, it also means I should have 2, 1 being an element of R. So it is symmetric if for all XY element of X, if XY is an element of R, then YX is also an element of R. Then we move on to transitive. R is transitive. R is transitive if for all X, Y, Z elements of X, if XY is an element of R, comma, YZ is also an element of R, then XZ is also XZ is also an element of R. So we have got transitive relation. If XY is an element of R and YZ is an element of R, then XZ is also an element of R. The formation of XZ is hinged on the relation that exists between Y and Z and Y and X. It's like transitive in terms of if we have got two people that are playing together as friends, that's X and Y, right? For example. But Y has got his own other friend who is not X, that's Z. Then X and Z can also play together at some point, basing their relation on Y. So if I have got 1, 3, and I have got 3, 4, then I can come up with 1, 4, basing on 3. Let's try to. So your task is to make sure that you verify these relations when you are given a question, it should satisfy all three conditions if it is an equivalent relation. If it does not satisfy one, then it's no longer an equivalent relation. But you don't stop testing. You have to test each and every condition for you to get the maximum marks. Right, we can look at an example. We can look at an example. The relation R on a set A, where A is equal to 1, 2, 3, until I reach 14, is defined as R is equal to xy such that 3x minus y is equal to 0. Then find R, then verify if R is an equivalence relation. Right. So you've got two tasks there. The first task is to find what R is, and the second task is to come up with to verify the three conditions if R is an equivalence relation. So you are given a condition on how you come up with your R. R is consists of xy provided that right, provided that they meet that the condition of that equation, 3x minus y is equal to 0. So I'm coming up with R now. I'm going to have the first element is 1, 3, for obvious reasons, because it satisfies that condition. Then I'm also going to take 2, 6. I'm also going to take 3, 9. I'm also going to take 4, 12. Then I'll stop there. Ordinarily, the next one would have been 3. It would have been what? It would have been 5 and 15, but 15 is no longer part of our set. So that is R. That is R with those elements. Right? If you don't know how we came up with R, then you are in trouble there. But I think everything else is clear because we are just satisfying this condition based on the set A. Right. So I can start to verify the transitive issue or the reflexive issue. If I pick, because from the set, I know that for transitive, for issues of reflexiveness, because what we know is that R is a subset, right? But I know that it's x comma x to be an element of R. So I need to find elements like 1, 1. I need to find elements like 2, 2. I need to find elements like 3, 3. I need to find elements like 4, 4. And so I go on like that to meet the reflexiveness. But so far, I don't have those. So it is, I'll pick one of them. Since, for example, 2, 2 is not an element of R, so R is not reflexive. I'll move on to what I have on the set, right? Symmetric, it says XY, then I should also have yx. So I'll pick one of those elements in the set R. For example, 1, 3 is an element of R, but 3, 1 is not an element of R. So basing on this, which is the element of R, I don't have 3, 1. Even if I pick 2, 6, I don't have 6, 2. Even if I pick 3, 9, I don't have 9, 3 for this condition of symmetric to be satisfied. So I will pick 1, then I can actually say that R again is not symmetric. I'll move on to the last condition, transitive. We know that it's X and Y, then Y and Z, then we can have X and Z, where we say that their relation is based on that. So I'll pick 1 and 3, right? 1 and 3 is an element of R. The next one that I have to pick is one that starts with 3. I have got it. 3 and 9 is an element of R. But based on these ones, I can now say, but 1, 9 is not an element of R. But on this particular instance, then I can say that R is not transitive. So my final conclusion is that R is not an equivalence relation, because not only does it not satisfy once, but it does not satisfy all the conditions. So I can safely conclude that R is not an equivalence relation. So you are required to also test. You are required to also test these conditions one by one. Even if you see that R is not reflexive, we now know the conclusion, but go on and test symmetric, go on and test transitive. Then you can make a proper conclusion so that you get all the 4 marks. Because when we say 6 marks, prove that R, verify if R is an equivalent relation for 6 marks, you are supposed to test for each of those 3 so that you get 4 marks. Going to conclude that R is not an equivalent relation is okay, it's correct, but you'll not get 4 marks. And you fool yourself and your friend that my equivalent relation no pandaroa much. Then when results come, to register food. Right. So this course is the highest failure rate. On average, if you are not someone who is working hard, you take it not less than 2 times. You take it not less than 2 times. But if you are working a bit hard, you will be able to take it once, then you go. But if not, I'll tell you, state chingori pano chingokuzokorodzesa saizvozvizvo. Right, let's move on. So I'm moving on to inverse relation. Inverse relation, which is another area that we can quickly look at. If R is a relation from X to Y, then the inverse of R is the relation, then the inverse of R is the relation r to the power minus 1 like that, which is again a subset of y Cartesian product x. Because r is a relation from x to y, which means it's the Cartesian product, it's from x to y, and r is a subset to that. So the inverse of r is a relation which is also a subset of y Cartesian product x, where obviously defined by, obviously this one is defined by x is defined by yx being an element of r inverse if and only if xy is also an element of r. It only becomes an inverse of r if and only if xy is also an element of r. So if I have got x, set x, for example, I can have set x with 1, 2, 3 elements. Then I can also have set y with elements a and b, for example. So I can find r here, right, where I'm just going to perform a Cartesian product of that. I don't want to worry much about the condition of coming up with r, for example, 1a, 1b, for example, right? If I want, then I can actually come up with the 2a, then I can come up with maybe 3b, for example, just for an example. Then what it means is that the inverse of r is still a set a1, b1, a2, b2, b3. Then, so we are just saying that for this one, once you have got your element coming up with r, then the inverse is just that you can play around with that one, then the rest will be history. I want to define a composite relation. If R1, for example, is a subset of x Cartesian product y, a and b there, and R2 is another subset of y Cartesian product z, then the composition of R1 and R2, for example, is the relation R2 composite R1. Here the order of representation matters. The way you represent them, from here is also a subset of X Cartesian product. So your relation there, you see when we cover functions, composite functions, these things, they matter in terms of how you represent them there, right? Obviously, provided X and Z are elements of the composite relation, if and only if maybe there exists a Y, where we are saying that they are being linked by Y, because this one is more or less the same as the transitive. The composite relation is coming up because R1 is a subset of the Cartesian product X cross Y. R2 is a subset of Y cross Z. Then we are coming up with the composite relation based on the subset of X and Z. And X and Z are being linked by Y. That's why we say there exists a y element of y such that xy, for example, is an element of R and yz is an element of R2, R1 and R2 in that fashion. So you can come up with a composite relation, but your composite relation is based on the relationship that exists between x and y and z. So x and z can come up with a composite relation or because of y, like what we saw the other time when we were covering transitive relations. Let's try to look at an example. Let's try to look at an example. So if I have got x, the set x with elements 1, 2, 3, then I have got y with elements A and B, then I still have got z with elements capital letter A, capital letter B, and capital letter C, like that. And I'm also given that R1 is a relation with 1A, 2B, 3A, 3B. Then I'm also given that R2 is a relation with small letter A, capital letter B, A and C, and B and A. Then if I'm going to find the composite relation, right? So I can find the composite relation where the order is of paramount importance here. So what I'll do is in your module, I think there is this concept, but what they do is they put like sets there, another set there, another set there. Then they try to draw lines linking each other so that you can link this one and this one. I think that's the method they use. Still a good method to adopt in case you meet these things. Still a good method to adopt in case you meet them. But I'm going to just use a simple method that I also find comfortable in using. So what I'm going to do is I'm going to go where R1 is. Then I'm going to trace using those things, right? Because if this is XY and this is YZ, then I can come up with XZ based on the relationship that exists. So I'll go element by element in trying to trace those. So I'll start with this one. 1A, is there anyone that starts with an A there is there? So I have 1B, for example. I have that one, so I have 1C. Then there's nothing there. I go to 2B, then I can have 2A, 2A. Then I am done there. I go to 3A. 3A, I can still come up with a 3B. 3B. Then I can come up with 3C. Then I can go to 3B. 3B. There's nothing there. There's nothing there. Then I can have 3A. Then I can stop. So that's how you come up with your composite relation. There is also a section on power relations, which I am not going to take you through because we've rested it for this examination period. We've rested it for this examination period. Right. So let's try to look at things that let's look at functions. Let's look at functions. So a function is a way of matching, right? The members of set A, set A to a set B in its simplest definition, right? In its simplest definition. Now, there are things that you need to worry about on functions. A function is not a function. There are things that, so if I've got set A there, I've got set B there, right? I've got set A, I've got set B. There has to be a criteria in which I can use to match the elements of set A to members of set B, right? Now, there are things that you need to remember. That a general function, it will point from each member of A, obviously, to member of B, right? So when we're dealing with functions, a function is not one to many, then it ceases to be a function. Right. So what it means is that you cannot have f of x being equal to 7 or 9. What it means is that whatever the values of x that you feed in here, you cannot have one going to 7, one going to 9. So a function is not one to many, which means from one value you cannot go to many values, but it can be many to one. So these are just principles that guide you to understand the functionalities of function. So the moment you find yourself having one to many, then you have to stop. You are no longer dealing with the function. But many to one is okay. Let's try to look at 3 different types of functions that I want you to have. Let's look at the injective, which is a one-to-one. Injective. What it means is that every member of A has its own unique matching member of B. Every member of A has its own unique matching member of B. Right. So every member of A has its own unique matching member of B. That's your injective function, or it is called a one-to-one. What it means is that I can have members from A like that, and I can also have members from B like that. Since it is a one-to-one function, every member of A will have its own unique matching member of B. So I can have this one going there, that one going there, that one going there, and that one going there. Every member of A. Even if I still have got a B that is not matched here, it will not matter because every member of A has its own unique matching member of B. That's a one-to-one function. So what does it mean when want to prove this. So in essence, symbolically it means that right, f of x is equal to f of y. F of y. This is what it means. F of x is equal to f of y, therefore x is equals to y. For every member of x, it has got its own unique matching member of y. So once you are given a function, you are supposed to, if you are checking if it is an injective function, for example, let I'm going to let f of x be equal to maybe, for example, 3x plus 7, for example, right? Then I can now go on to say, if I want to verify if this one is an injective function, what it means is I'm going to say f of x is equal to f of y, then 3x plus 7. It should have another one called 3y plus 7, like that. Then I reduce that one. Then I was at some point I have 3x equals to 3y. Then I have x is equals to 1. Then I can stop like that to say that this one is a one-to-one function. I should be able to reduce whatever I am given. But you start by identifying that f of x is equal to f of y. Then you come up with an f of y, which is the question that you are given, but you express it in terms of y. You reduce whatever you are given, both sides, until you have got x is equals to y. Then you stop. You have actually satisfied the conditions that for every member of A, there is a unique matching member of Y. So if we go back to a question in the assignment where we dealt with f of, was it x squared? F of x is equals to x squared, right? What it means is that x squared, let's try to just squeeze it in here. We have x squared being equal to y squared. But x is equal to positive or negative the square root of y squared, which is x is equals to positive or negative y. Ordinarily, it's just that I saw what the tutor was giving marks for on that, because there are two values of y there. And the other one is positive y, the other one is negative y. Right. So it's not an injective function. It's not an injective function. All right, it's a story for another day. If you got the marks, you got the marks. Right. But that's how you deal with it. Let's move on to subjective. Onto. The subjective means that every B, like notice the order in which way we are expressing them, has at least, or every member of B has at least one matching A, or member of A. Then another point to note is there won't be a B left out. A B left out. Right. So what you need to worry about, because if you saw the diagram that we drew on injective, there was a B, a member of B that was lying. It didn't matter. Why? Because we are saying that every member of A should have its own unique matching member of B, and all the members of A, 4 of them, they're unique matching members of what? Of B, right? But here we are saying that every B has at least one matching A, which means there won't be a B left out, right? So we can now introduce, or we can now demonstrate the issue of many to one, that we've been talking about, and it still remains a function. So I can decide to have 1, 2, 3, 4, 5 members of A. Then I can have 4 members of B. Then I can try to have many to 1 on that particular instance. I can have these ones going there. Then I can have that. I can have that. I can have that. There won't be a B left out, but I can demonstrate the issue of many to 1 here, and it still remains a function. What we are not allowed to do is to have 1 to many. It ceases to be a function. Like what we were talking about when X can take 2 values of Y. The other one is positive Y. The other one is negative Y. So that's your injective. That's your injective. Look at that. Look at that as part of your onto. Now, what it means symbolically is that f of x should be equal to y. Remember, injective f of x is equal to f of y. Then surjective or the onto, we are saying that f of x rather, is equal to y. So whatever you're given, you put it in terms of y. Then you try to make x subject of the formula. You substitute back into the equation. Then the equation actually comes out as a trivial kind of a proof, whereby you are zeroing around the same kind of proof where you are making this one a subject of the formula. Then you later substitute it back into the equation that you want. But that's the generic proof for onto. What you are given, express it or equal it to y. Then you try to make x subject of the formula. Then you try to resubstitute back the calculated value of x into the original equation, so that finally at some point you have got your what, your y there, which will result as your solution in terms of f of x is equal to y. So bijection, if I want to quickly jump into bijection here. Bijection, which means both injective and surjective. They are both injective and surjective. They are both injective and surjective, right? So if we want to define it, we are saying that there is a perfect one-to-one correspondence between the matching members of the set. Perfect one-to-one correspondence. On injective, we had a B that was not matched. On surjective, we had a many-to-one. But on bijective now, we have got a perfect one-to-one correspondence between the members of the set. If you have got 4 members of A, they also should have 4 members of B, perfect one-to-one correspondence. So to verify if a function is bijective, you are supposed to go through the injective first, then the surjective second. If these conditions are satisfied, then you can conclude that the function that you're dealing with is bijective. If it does not satisfy on one, you don't stop there. You have got to verify the other part. But the conclusion is that it's not a bijective function because it does not satisfy both conditions. So once I test for injectiveness and I find that this function is not injective, I go on again and test for surjective so that I make a proper conclusion based on that. But if it does not satisfy one, then it means that it's not a bijective function. So those are the things that you want to worry about on types of functions that I also want you to have. Let's try to move on and attend to other functions on that. Maybe before I jump to composite functions or inverse functions, then I want to quickly look at the domain and the range. So your domain is a set of input values. Your domain is a set of input values. The values that you put into a function, and that function still remains a defined function or a function within acceptable parameters, right? Then you can have your range. Your range is a set of output values. Right? Or you can want to look even at the codomain, possible output values, right? But your domain and your range is the things that you can really worry about. So if you are given a function, for example, f of x is equals to what? To the square root of x minus 7. Then we are told to find the domain. For example, the square root of x minus 7. Then we are told to find the domain. What we know is that for those values, for that function to continue to be defined, what it means is that we will still need positive numbers inside that function, inside that square root, because we are not dealing with complex numbers here where we accepted negative numbers, like a story for another day. But for this course, we want to find the value of x that maintains that positiveness that we want inside this function. So you are going to define your domain, a set of input values. What input values of x can you put so that this function continues to be defined? Else, if it becomes a negative value, then it's out of range, provided we're not dealing with complex numbers. So that's how you come up with your input values. Then you can actually generalize what input values are we talking about. So numbers like 6, numbers like 5, numbers like 4, and as we go on to negative infinity, right, like that, these values, they will produce a negative value inside that square root, and we don't want that. So I can generalize to say that provided a number is smaller, right? So the set of input values there is just to say a number should be greater than or equal to 7. I can come up with a domain like this. So that x for this function, what input values am I putting? I'm putting x greater than or equal to 7, which means I can have 7, it's 0. I can have 8, 9, 10, as we go on like that. Then this function is defined in that range. So I can generalize my domain to just say that x should be greater or equal to 7. What I don't want is anything like 6, 5, 4, and we go on to negative infinity in terms of those integer values there. So I can define my domain like that. X should be greater than or equal to 7. I can start with 7 itself. Then it's the square root of 0 is 0. I can go to 8. I can go to 9. I can go to 10. I can go to 100. Anything above equal or greater to 7, it's acceptable. Right. Let's move on. We've got a lot of things to cover. I told those that were early is that I don't promise to cover everything, but I'll cover until I'm tired. When I'm tired, I'll tell you I'm tired and I'm stopping. But for now, let's try to see how best we can cover this. Let's look at inverse function. Let's look at inverse function. Right. So you've got your inverse function there. So if f of x is equals to okay, later we're going to let f of x be the function, right? Then the inverse function, which is obviously denoted by like that, f to the power minus 1 of x, like that. Inverse function, which is denoted by that, has got a series of steps that you want to know if you are going to find the inverse function. Number one, you're going to let f of x be equal to y. Then number two, you can still make x a subject of the formula. Number three, you are going to interchange x and y. Then number four, the expression in y is your inverse of x. So you need those things in place for you to be able to calculate the inverse function. The first thing is you're going to let f of x be equal to y, whatever you are given on that question. The second thing is you are going to make x subject of the formula. Then from there you are going to interchange x and y. Then the expression in y, in y is actually your inverse function that you're looking for, right? So we can have an example. We can have an example where we say that we try to put that into practice. Try to put that into practice. So we can quickly look at f of x is equal to 1 over x minus 2, like that. This is the expression that we have, and our requirement is to find the inverse function of this function, 1 over x minus 2, right, like that. So we can let y be equal to f of x, or f of x be equal to y. So we are saying that y is equal to 1 over x minus 2, like that. Then the next step is that we want to make x subject of the formula. So y plus 2 is equals to 1 over x. Then I can multiply both sides by x if I want. I can multiply both sides by x. So at some point I'm going to have x bracket y plus 2 is equals to 1. Then I can have xy plus 2x is equals to what? Is equals to 1. Then I can factor out x, y plus 2 is equals to 1. Then I can have what? I can have x is equals to 1 over y plus 2, which I could easily do earlier by just jumping steps, but I just wanted to demonstrate. Then we interchange x and y, so y is equals to 1 over x plus 2. So the inverse function was, we said that the last step that expression in y is actually equal to 1 over x plus 2, like that. So that becomes your inverse function. That becomes your inverse function. So that's how you come up with your inverse function. What you need to know, the steps. The first thing you're going to make, whatever you're given, you're going to let it be equal to y. Then you're going to now make x subject of the formula. You're going to interchange x and y. Then you are going to finally have that expression in y is actually your inverse function. I'll have one last one on inverse function, then we move on to composite function, which you can actually look at later on with your friends. I'll have h of x, for example, being equal to 2 to the power 3 plus 3. Your requirement again is to look at the inverse function of that expression. The inverse function of that expression. So the first thing is going to let y be equal to that to the power 3. The other thing is to make x subject of the formula. Y minus 3 is equals to 2x to the power 3. I'm dividing both sides by 2 rather. Y minus 3 over 2 is equals to x to the power 3. Then I'm going to have x being equal to the cube root of y minus 3 over 2. Then I'm interchanging x and y. Y is equals to actually the cube root of x minus 3 over 2. So the inverse function of this one should be x. Let's see if we got that one correct. Right, so that should be your cube root of x minus 3 over 2. So that's your inverse function there. If you want, you can still further play around with it. X minus 3 over 2 to the power 1 over 3. You can still play around with it. That should be enough. I open to your inverse function. The rest is not important, but to know the steps so that you can change your subject or formula is obviously it's unfortunate. No one is going to teach you that because the green book is already done justice. But if you have forgotten, you can still go and steal your young brother's book or your young sister's book, reading the blankets covering your head, change of subject or formula, because you don't want your young sister or your young brother to know that at university level still you can't make a change of subject or formula. You can do that Nicodemously. All right, that's fine. Let's move on to inverse functions. To inverse functions. Inverse functions we've done. Let's move on to composite functions. Composite functions. So if I have got f of x and g of x, for example, b are the two functions. The composite function denoted by f of g of x like that. Remember, your composite function has a small zero which is not shaded, just a small zero which is not shaded like that. So that one is f of g of x. That's the composite function. Is found by or is calculated by taking g of x and substituting it into f of x where there is an x. So these definitions, it's like you are thinking in short. Then because when you try to remember what these other texts say about composite functions, you can actually find yourself hitting into problems. But if you remember this one, because the one that is written after the function, the composite sign, is the one that you take and you put it into one that is written before. Like in this case, f of g of x. You are taking g of x, substituting it into f of x, where there is an x. So every part of f of x where there is an x, you are substituting it with g of x. So it applies for any other anything that is written after the composite function. You take that one, you put it inside the one that is written before the composite sign. Everywhere there is an x, you can remember that. These are not definitions you will find somewhere. These are just definitions that make you remember the process that you are supposed to do, right? So you are taking the one that is written after the composite function, in this case g of x. You take that one, you substitute it into f of x, but you're putting it everywhere there is an x in f of x. That's where you put that whole function, So I can quickly look at an example. Where I have f of x to be equal to x plus 4 and g of x to be equal to x minus 4, for example. Then I'm supposed to calculate f of g of x, or I can also calculate g of f of x. So these two examples should suffice in terms of you understanding how you maneuver your way around composite functions. So let's start with the first one. The first one, we are taking g of x, substituting it into f of x every time there's an x. So what it means is that f of g of x is equal to x minus 4 plus 4. This is x. G of f x is the same as saying x we are taking now f of x into that is the same as x plus 4 minus 4, which is again x. But maybe for argument's sake, let's have another one so that people can really see what we are trying to do. So I can have f of x, x squared minus 4x plus 4. Then g of x, I can have that is x plus 1, right? Then I'm supposed to calculate f of g of x. So I'm taking g of x, I'm substituting it everywhere there's an x. So ordinarily I should have x plus 1 squared minus 4 bracket x plus 1 plus 4. I'm trying to expand that one. That should be x squared plus 2x plus 1 minus 4x minus 4 plus 4. So I have got x squared minus 2x plus 1. That is if we did not make any errors there. I think that should be okay. That should be okay. So that's your f of g of x. If I want, I can still substitute. If I want, I can still find g of f of x. I can still find that one easily without any problems. Without any problems. Without any problems. So that's it on your functions. That's it on your functions. That's it on your functions. Right. I think we are okay on functions. I'll try to move on to propositional logic. To propositional logic. We will not be able to get everything in one day, especially if you haven't been reading. Then it becomes an uphill task. It becomes an uphill task. Right. Propositional logic. Propositional logic. Propositional logic. Now, there are things that you need to know. There is what I call prior knowledge that I expect from people that have been doing the course, that have been submitting assignments. Obviously, in either you were doing the assignment yourself or you were copying from your friend, it will not matter now. What matters is that I'm assuming that people have been working, people have been doing some work prior to this tutorial. So I'm coming in with that assumption that you've gone through your module. There are areas, obviously, that are difficult to grasp, but well, apana ekutamba, we are just trying to cover a few more things before I get tired, right? So let's try to look at what we call logical connectives. Logical connectives. Logical connectives. Logical connectives. Now, your logical connectives, these are symbols. We have got what we mean. We'll just come up with a small table. I'll just come up with a small table. The connection, right? Then I'll come with a meaning. Then I'll come with a symbol. Right. So there are 4 logical connectives that I want you to have, or you already have, but we're just trying to shed a bit of light into that. We have got what we call as the negation, right? Its meaning is not, its symbol is just that. Then we have got what we call the conjunction. The conjunction, right? Then its meaning is and, right? Its symbol is this, like a upside down V. Then we have got what we call the disjunction. Its meaning is O. It's like a V like that. Then finally, we have got, not finally, but maybe one more. We have got what we call the conditional. Right? Obviously, its meaning is if, then its symbol is that arrow, Then we have got what we call the biconditional. Its meaning is the if and only if and only if and only if. And its meaning is a double-headed arrow. double-headed R. Right. So no one is going to tell you about this. No one is going to tell you about this, but someone is going to tell you about this. Right. But this is the background information that you need to have. You need to know the negation, which is the not. You need to know the condition, the conjunction, which is the and. You need to know the disjunction, which is the or. You need to know the conditional, which is the if then. Then you need to know the biconditional, which is the if and only if. Now, each of these has got its own truth tables, which is in the module, right? It's good to cram each and every truth table in the module under these sections, but it's more nicer to know how to come up with that truth table. Because if you cram and you don't understand, the issue is when you get to an exam, you encounter a problem like you will in a few weeks, then you will be stuck now to say, how do I come up with this? But if you know, because what it means is you have to download all the 5 truth tables first that you have crammed somewhere, write them somewhere. Then you try now to match and come up with that truth table or those questions that you will be required. But if you understand how to come up with those truth table, it means you don't have to claim anything. You know the truth table, how you come up with, provided you have got the meanings of those things. I'll start with the negation. Negation. So if I've got let me the way you come up with truth tables, there is a formula to that in terms of the number of rows that you want. 2 to the power n, like this. 2 to the power n, where n is the number of variables in the expression. Okay, number of variables in the expression. What do I mean when I say the number of unique variables? Let's start with the negation, then we'll come back to that. So the negation, I don't have to worry much about it because it's quite simple. It's quite simple. I need 2 rows for that. So I'll have my negation like that. I need 2 rows. I'll need 2 rows for that negation, right? So I can have 1 unique variable p, right? Its negation is not p, right? So if I have got a true, its negation is false. If I have got a false, its negation is true. Now, here, these are unique variables that I was talking about. If I've got only p that I need, it means 2 to the power 1, so I'm going to have 2 rows. It helps you when you're dealing with 4, it helps you when you're dealing with 2 variables, 3 variables, like what you encounter in the assignment or in the coming exam. You are supposed to have 3 variables where you deal with PQR, then you come up with 8 corresponding rows, then you work yourself out, right? So we can still look at the next one. I'll try to squeeze in here, right? The next one was let's look at the disjunction, right? So P, right? And Q, P, Q. Okay, I'll have a small letter Q, like that. You know, again. So P or Q, right, like that. P or Q. So I'm going to have I'm going to have let me see if I can. Okay, partly I think people can see partly. Right. True, 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 false, false, true, false, false. You don't have to claim those. Because the reason why I'm putting 4 rows here, I've got P and Q. So it's 2 to the power 2. These are the 2 unique variables that are there. So it will give you 4. Then you know that I have a true, 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 false, false, true, false, false. Then you can come up with that. So this is the disjunction, the O. So your O, another way to remember it, it becomes handy when you're dealing with Boolean algebra. Right. It's important to note when we are under propositional logic, trying to come up with ones and zeros, use true and false. Ones and zeros, use them under Boolean algebra. Right. Let's use true and false there. So your T, this is something aside, right, that you can actually help you. If you are starting, you need something to like boost your memory or to cram or something. Right. Generally, your T is like a 1, okay? Your F is like a 0. Somewhere, this is aside, right? Then your O, we know it's like a plus. Your O is like a plus. So T and T is T, right? T and F is T. For O, the disjunction. F and T is T, then F and F is what? It's F. It's like in your mind, you're just saying 1 and 0, 0 and 1. But also T 1 and 1 and 2. Kadaro manje, because I am against kadaro manje, then you're in trouble. All right, I'll go to the conjunction, the end. Just trying to squeeze a few more lines there before I go to the next page. P and Q. If you write the examination that I think you will write, number one, it will ask you to come up with a truth table. Number 1, so I think B, B, yakutoda kuti ungochiziva zvinizvo. Sikaioregedza kubva wapusa, wabva watoomera wototi ndatomerwa ini ndatoshaya kuti ndoita sei. Totogara ndakudini? Ndakutipa. Right, PQ, P and Q. So remember, and is like your multiply. We know this from sets, we know this from things that we've been dealing with earlier. So true, 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 false, false, true, false, false. So I can fill in the truth table. This is true, this is false, this is false, this is false. Remember, it's an end.
Yeah,
it's a multiply.
so when someone is sharing their video.
Kumana mushare vakanditi muona kuti tachitaura paipendi. Isati singasweleleka vanhu vanoshare. Abva kuti kwanonzi chari wabva nepi nai. Rekedza kuti kutamba kati tiri pabasa kanditi vanhu vakatenga data here. Saka vanhu varida kuziya ka varida kuona iwo vakauya uchida kushare manje. Then it's trouble. Zvadzoka.
Yeah.
Right. So that's what you have there. That's what you have there. These things you already have them somewhere within your truth table, within your module, right? So it's important that you also know how you are coming up with that. Also know how you are coming up with that. Right. So there are interesting facts on the conditional. Then we'll finish with the biconditional. These tables, you already have got them in your module, but I'm just trying to shed a bit of light in terms of how you not ordinarily come up with those tables, so that you don't kill yourself cramming. You don't have to cram, but you just have to know what you're dealing with. Right, so the conditional P, Q, P implies Q. right. Now, the conditional, it becomes false once when you have got a T and an F, otherwise it is true. These are the things that you need to remember to go around it. The conditional, it becomes false once when we have got a TF, provided the T belongs to P, the F belongs to Q, in that order, right? So otherwise it is what it is true. So I'll just go and put a false there, then I'll put a true. That's the conditional. Then biconditional, P, Q, P if and only if Q. So that you can still cram if you want to cram. I have no problems with that. I'm not going to ask you come up with a conditional. No, you are going to apply. Right. So this is the biconditional: true, 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 false, false, true, false, false. Right. So this one becomes true when P and Q are the same. Otherwise, it is false. It becomes true when P and Q are the same. Otherwise, it is false. So when a P and a Q are the same, it becomes true. When they are different, it becomes false. When they are the same, it becomes true, like that. So that's basically it on how you come up with those. A point to note is on the conditional. It becomes false once when you've got a TF, provided the T belongs to P, the F belongs to Q in that manner. Which means the moment we shift to Q implies P, we are still looking for a TF, but this time the T is for Q, the F is for P. So it's important to recall those things. Right, let's move on to areas of application. Now, you can be asked to come up with a truth table, for example, to check the equivalence of two functions. It's important that you recall these truth tables. Like, for example, I can say that verify if these things are equivalent. P, if and only if Q is equivalent to P, implies Q, and Q implies P. So that equivalent sign, it means that what you want to do there is you want to come up with a truth table, and you want to make sure that the rows that you've got P implies Q and Q implies P are the same as the rows with P if and only if Q. So what you are going to do there is you are going to go step by step, coming up so that you don't miss it. You don't miss things that are important. One of the things that you need to remember is do not negate anything that you don't have a column for. If you go back to the column in negation, table negation, we first had P, then we had not P. Do not start with not P if you don't have P. Izvozvo zvinoitwa nemunhu akuziva zvinhu zvaanenge achiita. Otherwise, kana uchiri kutanga, you are going to make errors. Now, I see there are two variables that are unique, P and Q. What it means is that on my truth table, I'm going to have 4 rows because it's only P and Q. The moment you have got R, then you have got 8 rows, right? So P, Q, four rows, right? Step by step, right? Ordinarily, what I want is I want you, but if you are starting, you can do what I'm doing. But if you are now a pro, I mean you can do other ways. On the left hand side, I see there's a P if and N, if and N, if Q. So I can write that one so that I don't miss a thing. I go to P implies Q. P implies Q. It's a separate column. Q implies P. It's a separate column. Then I have got now P implies Q and Q implies P. So the rows that I'm supposed to compare are these ones. So these are the rows that I'm supposed to compare. So I'm starting true, 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 false, false, true, false, false. Is there a particular order in writing these things? There's no particular order. We are adhering to this because you are still starting, right? False, false, and anyhow. You're going to anyhow. And then, right. We know P if and only if Q, we know what it means. So if this one becomes true when they are the same, so it's true, it's false, it's true. P implies Q. I go where P is, I go where Q is, right? It's a true, true. It becomes false once when we have got a T and an F. I'll quickly put in a false there, then it becomes what? It becomes true. Q implies P. I'm now starting with what? Q going to P. So Q implies P. Q going to P. So I'm looking for a TF here. TF here. Because I'm now starting with Q. It's again a T and an F. It becomes false. Otherwise, it is what? It is true. Then I now join P implies Q. I go to the row where P implies Q is. Q implies P. I go to the row where I touch them now. Right? They are being joined by an end. I know an end is a plus in my back, in the back of my head. T and T, that one is a T. False and T, that one is a false. T and false, that one is a false. T and T, that one is a what? It's a T. So I can now see that, wow, they are equivalent because the columns of these ones, they are the same. It means that these ones are equivalent indeed. You should be able to follow that with no problems at all. Let's attack the last thing that is coming and that you saw on the assignment. I think on assignment 2, where you are going to prove the validity of a statement or of an argument. Let's take down a few things so that we know we are in the same manner, in the same. So an argument is a list of statements, right? An argument is a list of statements called premises, the assumptions or the hypothesis, followed by a statement called the conclusion. So an argument, when we say verify if an argument is valid, we are saying that an argument is a list of statements, right? The list of statements is called the premises. Then it has got what we call assumptions or the hypothesis. Then it is followed by a statement called a conclusion. Now, it's important. It's important when you are dealing with those things. When you are dealing with those things. So I'll show you what we call the premises. I'll show you what we call the conclusion. So if I have got a list of premises. These are conditions. These are conditions that I can write. I can write premises there. Then once I have got a line like that, in a statement, it usually comes as the therefore. Therefore, this line or the therefore word, it means everything that is coming under the therefore, after the therefore, is now the conclusion. Or if you see a line, everything that is coming below the line is now the conclusion. It's important because you are going to break down a problem that you are given, so that we're using a series of steps, so that you have got what we call the premises, then you have got what we call the conclusion, and you're still going to build those things in terms of what we call the premises and what we call the conclusion. In a story like problem, you are looking for the word therefore. Anything that is written before the therefore constitutes your premise. Anything that is written after the therefore constitutes your conclusion. So these are important things that you need to worry about. Right, let's try to look at a few things. Then we try to attend to particular problems. Now, an argument is said to be valid if all the critical rows in the conclusion has truth values of t. An argument is said to be valid if all the critical rows in the conclusion has truth values of t. Then we can say, this argument is valid. An argument is said to be valid if all the truth values in the conclusion column has truth values of t, right? So what is a critical row? A critical row is a row in a truth table. A critical row is a row in a truth table where the premise have truth values of t. The premise has truth values of t, it becomes a critical row. So in a truth table, you can have two critical rows, right? The premise, anything that is written before the conclusion, has truth values of t. Then an argument is said to be valid if the conclusion in the critical rows, right, has truth values of t. So truth values, critical rows, right, these are rows where the premise have truth values of t. But the critical row that an argument is said to be valid if in the critical row the conclusion now is truth values of t. So we are dealing with critical rows. Yeah, we are dealing with critical rows. That's what we are dealing with. Let's try to have an example where we come up with what we are talking about. So it's important that you identify what's your premise, what's your conclusion. And when you're answering that kind of a problem, you are supposed to follow the fashion that we are going to put there for you to get maximum marks. So you are given a series of statements. If, for example, if Tari is on team A, if Tari is on team A, then Hilton is on team B, then Hilton is on team B. Right? If Newton is not, if Newton is not on team B, on team B, then Tari is on team A, then Tari is on team A. So if Newton is not on team B, then Tari is on team A. Therefore, I'm just going to shorten the therefore with those three dots. Therefore, Tari is not on team A, or it's not on team A, or Newton is not on team B, or Newton is not on team B, like that. So let's try to take it again so that we follow. If Tari is not on team A, then Newton is on team B. If Newton is not on team B, then Tari is on team A. Therefore, Tari is not on team A, or Newton is not on team B. Right, verify if the argument is valid. That is the question. Verify if. So what we need to do is we need to come up with logical equivalencies of those statements, because we will not be able to come up with a truth table if you have got those statements. What we need to do is to equate symbols that we know P, Q, R to those statements. Now, we see the word if, and we also see the word then. We now know P implies Q. If P, then Q. So we also see the word or. We know the logical connective that we need there is the disjunction. When you see maybe another word and, you know that on this part I'm supposed to use the conjunction. So that's how you come up with those things. So we can make a what? We can make a commitment to say that I'm going to let P be equal Tari, right? Is on team A, for example. Right? Then I'm also going to make a Q, for example, to say that Q is for Newton being on team B, for example. What it means is not P means that Tari is not on team A, not Q. It means Newton is not on team B from what we have. So I can start with the first statement. If Tari is on team A, that's P, then I now know it's this one. Newton is on team A. Let's if I want to take it again so that did we say if Tari is not on team A? Let's have maybe not here so that it comes out what we want. You can just add the not so that it comes out the way we want. If Tari is not on team A, then Newton is on team B. Then if Newton is not on team A, then Tari, yeah, it comes out like that. So let's have the not on the first statement. So it's not P implies Q, for example. We just added a not there, right, so that it comes out what we want. Then we can move on to the next statement. If Newton is not on team B, not Q, implies then Tari is on team A, it implies P. Therefore, I put a line to indicate I'm going to the conclusion. Therefore, Tari is not on team A. Tari is not on team A. That's what? Not P. Or, right? I put the disjunction. Or Newton is not on team B or not Q. Now, to reach that stage, like we have done, it has got its own marks. And once you fail to come up to that stage on whatever problem that you're working on, it means the truth table that you're going to come up with is a wrong truth table, right? What does it also mean? It also means that the conclusion in terms of argument validity, it's a wrong argument. It's a wrong conclusion. And barely you're going to scoop any marks from that question. Those questions, they come with 8, 7 or so marks. So it means you have lost everything. People, they find themselves in a comfort zone where they start to say, at least I don't go now to Nandazama. Apana chandinoona. Apana chandinoona. Right? Apana chandinoona. That's how people fail the course, because they move out of the exam room in comfort zone. Say, apa panongoona Nandazama. Apana chandinoona. Nokusiya wakadaro. Apana chandinoona futi. So make sure you've got your things in order so that you avoid carrying the course. Right. So let's work on that. So this is how you come up with those. So you follow the English statements that are there using the original table that I gave you under logical connectives. Follow the meaning, not right, and or if then, if and only if the biconditional. So you follow as you try to come up, then you label your things. Say this is my P, this is my Q, this is my R. So now, after I do that, let me come up with that same procedure. It helps you to identify what your premises are and what your conclusion is, so that when you go to the truth table, you can easily identify your critical rows where the premises are true, right? Then the conclusion in a critical row is true, then argument is valid. I want to use that same space to come up with the truth table. So I have got two variables, P and Q. So I'm going to have 4 rows. Right? True, 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 false, false, true, false, false. I go to the premise. I see that there is a not P, there is a not Q somewhere. So I will need a not P. I'm now writing not P because I have got P. Remember what I said. You cannot start to write not P without P. I can write a not Q because I've got Q. Then I go now to the premise. It says not P implies Q. I also go to another premise which says not Q implies P. Then I can go to the conclusion which says not P or not Q. Right. Then I can stop. That's how you fill in your columns. If you miss any column, it means your answer will be wrong. That's where problems will start. So I'm negating P. I go where P is. It's false, false, true, true. I'm negating Q. I go where Q is. False, true, false, true. Right? Not P implies Q. Now, it's important. Not P, right? Not P implies Q. I'm going to go where not P is, right? I'm going to go where not P is here. Then implies Q, where Q is. Quickly, I'm looking for a TF. TF, I have TF there. It becomes false. Otherwise, it is true. Hello? 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 Right. So I'm moving to not Q implies P, right? Where is not Q? Here implies P, right? So I'm looking for a TF, is there. It becomes false. Otherwise, it is true. Also, we are in the mark. Then not P or not Q. Here, right? That's an O. It's false. It's true. True. It's true. Like that. Now, after I've done that, I can now move on to worry about where are my critical rows? Truth values in the premise. Premise, these are the columns, right? Your critical rows, they've got truth values in the premise. My premise is the E in the E, so I come to these columns. I look for T and T. T and T, right? This one is a critical row. T and T, this one is a critical row. T and T, this one is a critical row. F and F, that one is not a critical row. Right. So in the premise, these ones, the ones that are written before the conclusion, right? On these ones, that's a critical row. I mark them like that. Now, an argument is valid if the conclusion, if the conclusion in a critical row is truth values. Now, this is the conclusion. I see a T there, I see a T there in the critical row, but there is an F there in one of the critical rows in the conclusion. So I can conclude that maybe because of row 1, which has got an F in the conclusion of a critical row, the argument is invalid. But if I had a T there, then all the truth values of T in a critical row, in a conclusion, if they were like that, then the argument was valid. So that's how you conclude. That's how you. So people have got a tendency to just say, they don't go to the argument is valid over here. No one is going to give you 8 marks for coming up with wrong things. No one is going to do that. You might have to redo the course until you get it right. We don't hesitate to, we have seen people failing for years. So I will not hesitate to make you one of them, as long as things are not in order there. I think, yeah. So you need to come up with the proper, you identify your P, you identify your Q, you identify your R in case maybe there's an R. You come up with those things. Then you identify your premise, you identify your conclusion. You come up with a truth table. You identify your critical rows. You identify your conclusion. You look for truth values in the conclusion. Then you make a proper conclusion in terms of if the argument is valid or not. That should be it on propositional logic. I think I've covered everything that you need to know on propositional logic. I'm trying my best to be as to explain as much as I can so that people can see what we are dealing with in that instance. Okay, so I want to move on to predicate logic. I'll stop at 4. That's when I'll stop. So 4 bars no I'll stop, but I don't know how much we would have covered, right? So I'm trying to cover as much as I can so that as no shikao to cover to cover. My tutorials ordinarily they have to be done twice, but we are doing it once. But let me go on to predicate logic. your predicate logic works like this. You are given a statement, right? You are given a statement, an English statement. Then you are supposed to come up with an equivalent predicate logic statement to that effect. You're given an English statement, then you're supposed to come up with an equivalent predicate logic. Now, there are things that you need also to know under predicate logic, right? There are things that you need to know under predicate logic. Right. They're what we call local and global variables. They're what we call local and global variables, right? So these variables, they'll help you to determine, right? To determine how you are going to structure your predicate logic, right? Now, you can have your for example, Zimbabwe is a country. Zimbabwe is a country, as an example. Now, if Zimbabwe is a country, okay, if I'm supposed to express that as a predicate, that statement, that English statement, if I'm supposed to convert that to a predicate statement, what I need is to identify what is a global variable, what is a specific or local variable, what is a specific example or local variable. What I will do is I'll put my global variable outside. I'll say country, in brackets, Zimbabwe. That's the equivalence of that. This country is the global, but Zimbabwe is a specific instance of a country. But it can apply to any other country, like South Africa, like Zambia, like Botswana, like Malawi. So ordinarily, we have country, for example, X, where X is a specific example. In this case, we are taking Zimbabwe. Right. So I can have another example to say John is tall, for example. John is tall. What it means is I should have a tall John. Because John is not the only tall person in the world, but specifically John here is tall. But I can talk of tall John. Right. So that's how you come up. So identify what is a global variable, what is a local variable, right? So I can say that for example, because for example, I can say that John, for example, loves Mary. Just for example, John loves Mary. Now, on that particular instance, what it means is what is the global variable? Love. Loves. Love. But I can move on to say love John Mary. Okay? Because the global variable that is joining the two is just love John Mary. So that I can generalize it to love XY, where I can also make room for you and your loved one. For you and your loved one. But love does not exist only between John and Mary. But for specifics, we can say love John Mary, right? But we can now generalize to say love XY, where X and Y is you and your loved one. So identifying what a global variable is and what a specific example is, it will actually help you in terms of what you really want to do there. Okay. Now let's move on. Let's move on to to other things on how you would come up with that. Now, there are what we call quantifiers in predicate logic. 3 important quantifiers. The first one is the universal quantifier. The universal quantifier. This is represented as for all. Now, what it means is that it takes words like all, it takes words like everyone, it takes words like anything that is universal in nature, that is inclusive in nature, it takes the universal quantifier, right? Then we also have got what we call the existential quantifier. The existential quantifier, right? With this symbol, they exist, some, part of, which means we are having a universal set, but from the universal set, we are taking a specific portion, which you are guided by words like some, part of, right? Or maybe whatever the case might be, right? But you be able to really see that here we are not talking about everyone. Then finally, we can work with the negation. The negation, we have worked with that. It actually means not, right? I can choose to use that one, or I can use that one, right? So those are the 3 things that you need to worry about. Those are the 3 things that you need to worry about. Now, ordinarily, the universal quantifier works with an arrow. They exist, works with the ampersand in terms of joining the connectives that you want to join. For all, usually it works with that arrow. The existential quantifier, it works with the ampersand that you can work with there. So those are the things that you can as well worry about. Now, for example, we can say that all girls love John, right? So what does it mean? It means that if you are a girl, then definitely you've got a thing for John, right? So I can now say from that I can say for all girls, X implies there's a love of X on John, like that. What I'm doing is I'm saying for all girls of X, right, we have got a universal set. It implies that you love X of John. Where I'm saying if I've got a set of girls, for example, it has got Mary, it has got Tendai, it has got Florence, Judith, etc. They come here on this X, where I'm leaving X John. Just like what we had Mary John on the previous example, where I said you can generalize it to love XY. We have got a Y already, which is John, but we can leave it open as X for where X is belonging to a universal set of girls. You can pick the name now to suit what you want to do. So that's how you generally come up with your predicate logic, your universal quantifiers, or if you want, we can have some girls love John. What it means is that there is a section that love John, but there's a section that do not love John, Right? It's no longer now automatic. Then I can now come with the existing child, because the moment I say some, which means that there exists a specific group that that love John, and some that do not even want to hear anything about John. So I can still have there exist girls of X ambassador love X and John, like that. Because the exist moves well with the ampersand. No girl loves John. I can just negate the everyone loves John there. All girls love John. I can just put a negation to that. Then my life will be easy in terms of that, right? So I can move on to say all frogs are green. Right, I'm out of paper. All frogs are green. Or then you have got your universal quantifier there, f of x, g of x. Then you should be able to. Right, as I try to look for another sheet of paper, we have got 30 more minutes. I'll be back. Let me just try to find out.
Guys, sukubatika here.
Uri kufila sei?
But zvese zviri kubatika vananyanya.
Kuneta vedu vetaneta.
So. Pandiri zvitori so.
Misa
But
dzizodurembesa guys.
Mangani mastanzi mangani kuna iwana?
But reason yepen nebepa ndaishaya because speed yacho ngonyora dhiva topa next topic.
Kana wemvunzo.
Haufaniri kunge uchifunga, haufaniri kunge unyora uzofunga afterwards.
Ainda tozvijaira ndaimboine ticha kadaro 11.
Yeah, but zotoita
Uzoti listen ukurekodha kwaka. Chinyarara eh.
Listen,
Anzi hapana kuzama. Andimake.
haungosii pari blank zvaunotrya something.
Musonokumbira mabhuku evanyenyu nayenyu manzwa kumachange of subjects.
Chikoro chevakuru all answers are correct wakomana musasiye pari blank mawo.
Istanza hakuna ari kuzama.
Apa haugoni kusiya pari blank. Apa izvo unosamisa lecturer otokupa 0 wanga uchifanira wana 3 marks. Musadaro.
Asi vakadziya sevanopedza mwana. Muchasvika here.
Kungovhundutsira kungoti munhu angonyora zvisvinhu chete.
Muri kurekodha ndisi.
As there have been many who have failed and I won't fear to put you on that list.
Kacha player record here.
Yeah. Chinyarara is good record guys.
Right, I'm back. Zvinhu kana zvisati zvaitika kwauri unofunga kuti hazviitike. That's the funny part. Inandimbofoirei. Zvakazvinzwa kakawanda izvi. You can even assess with the way you performed assignment. Ndopazvotombotangira. But anyway, let's push. Let's push. Right. So we're saying that all frogs are green. All frogs are green. All frogs are green. Then of x, f of x implies green x, like that. Some frogs are green, maybe they exist. And f of x ampersand green of x, right? Not all frogs are green. I can just negate, just move with one example that we can work with. I can even negate this one like that. So that's basically how you deal with those problems. Right. So you can still look for more examples with your friends, practice more examples, look for more work in terms of your practice. Then life should be easy, but you should be able to come up with correct predicate statements depending on what you are working on. You should be able to come up with those correct statements. I'll quickly look into series. Try to look into series. So if you are given the summation, because what we want on series is you should be able to appreciate the use of the summation sign. Maybe from r is equals to 1, r is equals to 4, then you have got half of r squared plus 1. Then you are told to evaluate such kind of a problem. Right. Once you are told to evaluate such kind of a problem, what it means is you are going to sum, because that one is the summation sign. You are going to perform a series of that function in r, but you're starting from r is equals to 1, and you are going to end at r is equals to 4. So what you are actually required to do, I can actually factor out a half. Then I move to 1 squared plus 1. Then plus, because of the summation sign, I move on to 2 squared plus 1 plus 3 squared plus 1 plus 4 squared plus 1. Then you move it like that. Then from there, you say 1 squared plus 1, that's 2, plus that's 4 plus 1, 5, plus that's 9 plus 1, 10, plus 16 plus 1, that's 17. So that's half, that's 27, 32, 34 of 34, which is equal to 17. So basically that's how you play around with those kind of problems, so you can actually find your answer there. These are, when you see such kind of problems, then you should be happy, because they just make you settle into the exam and trying to find marks that you can easily correct. Right. You are required to know arithmetic progression. You are required to know geometric progression, as I had also given in assignment number 1. So those formulas that are there in terms of your arithmetic progression, in terms of calculating the nth term for all integers, and calculating maybe the term of the series that you are looking at, because I am going to assume that for arithmetic progression for the nth, nth term. I'm just going to to let you know that this is also required. You can look at it. These are not in the module, so just like matrices are not in the module, you need to look at them separately from what you have in the module. This is obviously for n greater than or equal to 1, where a is the first term. So on this one, I can have my a1, for example, because this we are dealing with nth term. A1 is the first term, and a2 is the second term. As we go on like that, So it's important that that you also look at the third term until we reach the nth term. So a plus n minus 1 times d, where d is your common difference, and a is the first term of the arithmetic sequence that you're dealing with. So it actually helps you to find the nth term that you want. For example, if you were told to find for example, if you are told to find the 20th term, for example, the 20th term, you are told to find the 20th term of the arithmetic series, arithmetic sequence, for example, and then you are actually provided with the sequence. For example, if we have got 3, 9, then we also have got 15 and 21, and the list goes on like that. So when you are stuck, for example, it's better to understand the sequence. You write all the terms, then you come up with the 20th term. If you are stuck, like you don't remember the formula to calculate that, you can still get stuck in the examination, but you can even write. But if there are 100 terms now, if you have got the time, then you can still do it manually. But it's good to memorize the formula. Then you should be able to know what a is, what n is, etc., like that. So we told ourselves that a is the first term, so we know that 3 here, a is equals to 3. Then we want to find the common difference, which means we are going to say second term minus first term, or third term minus the second term, as we go on like that. So I'm just going to pick those two terms. I'm going to pick for d is equals to second term minus first term, so that I have got 6 there. This is how you play around with that, so that I've got 6 there as my common difference. Then the nth term that we want to calculate is 20 from this one. So I can easily now plug in to say that a of 20, which is what I want, is actually the first term, which is 3, plus n, which is 20, minus 1 times the common difference. In this case, it's 6. Right. So I can now play around with that. I think that one should be this is 1996. That should be 3 plus is it 114? I think. Then you can still work around to see that the 20th term is 117 if we are going to follow a difference of 6 going forward. Right? You can move on. You can move on to look at another value there. Another example where we say which term of the arithmetic sequence, which term of the arithmetic sequence, which term of the arithmetic sequence is 4 here. Then we also have got 1 and minus 1. Then now we have got minus 2. So we are saying the question is which term of the arithmetic sequence This is 77, right? Is a minus 77, minus 77, because we are still going to the negative. So we want to note minus 77 is which term, right? So we have got A as 4. We have got D, the common difference, second term minus first term, minus 3. I can still pick that one, 1 minus 4, so that I have got minus 3 there. Then I know that what I'm dealing with is minus 77. Because we want to look for n, but the term we already have is equal to Z4 plus bracket. The common difference is n there minus 1 times the common difference, which is minus 3 there. So I can play around with that. I can put the minus 4 there. So it's minus 77 minus 4, I think is equals to, then I can introduce minus 3n plus 3 if I want. So that one will give me minus 77 minus 4, is it minus 81? Minus 81, minus 81, minus 81. I can still bring that one this other side to make it minus 3 is minus 3 there. Then I can, is it minus 84? Minus 84, if I want being divided by minus 3, then whatever you get there, if I get these 2 remainder 2, then is it then is it 6? Is it 6 there to find the rest of I'm sure we can, if we did not make any errors there. That's 4 plus n minus 1 times d, which is minus 3. I can play around with this one, bring it there. Then I can introduce it there, minus 3n plus 3. Then that is minus 81. Then minus 3 minus 84 minus 3, something like that. And then we can solve for n. That is if we did not make any errors along the way. Now, so you can play around with, but the issue here is people should be able to understand how these things work, so that whatever solution, whatever you are given, you can still work it around. There are instances where you're supposed to come up with a simultaneous equation. Then you solve the simultaneous equation. Then you find your A, you find your D, you plug it into the formula, then you'll be able to find what you want to find. So later on with your friends, you can look at find the 36th term of the arithmetic sequence. You're looking for the 36th term of the arithmetic sequence, whose third term is 7 and eighth term is 17. Finding the 36th term of the arithmetic sequence, whose third term is 7 and his eighth term is 17. So you can work it around later on with your friends. I can look at the geometric progression. That one you are supposed to come up with 2 different equations, because you've got the sum, find the 36th term of the arithmetic progression, whose third term is 7, and the eighth term is 17. So you can play around with that. Okay. So so you can look at the geometric progression, the geometric sequence. I'm not worried about how you calculate until you reach the formula. I'm just worried about the AN, which is the nth term, which is equal to A, which is obviously the first term, R, the common ratio, n to the power n minus 1. So you should have your common ratio in place. Then n is the number of terms that we are looking at. Then you should be able to calculate the geometric progression or the geometric sequence. Now, so people can still look at those problems from different perspectives, so that you have what you need to have in terms of practice, in terms of working on those problems. We can have one example, or I can give you one example that you can look at with your friends, like find the eighth term of the following geometric sequence. Eighth term of the following geometric sequence for 12, then 36 and 108. 36, then 108. You're looking at the eighth term of that geometrical progression or the geometric sequence. So you can still identify what your common ratio is, identify what your n is, then identify your a is 4, which is the first term, plug in your values there, then you should be fine in terms of how you come up with those sequences. Because I've been checking what this guy who helps me in marking was doing, marking your assignments. I just saw that most of you guys, you got that part correct, which is a good thing. So I think people will be happy to continue practicing the geometric progression. Now, let's come in. Let's move on to attend to something else. That's okay. All right, so you can move on to look at that later on with your friends. I want to jump on to Boolean algebra. After Boolean algebra, if I still have good time, I'll do matrices. There are things that you need to know on Boolean algebra. You need to know the Boolean laws first, so that you'll be able to maneuver again in terms of solving. Remember, we have got set theory laws, and we also have got Boolean laws. They generally work hand in hand. Then the magic law is your De Morgan, right? It helps you to cover a lot of other things. So we know that in Boolean algebra, we know that a plus 0 is a. We know that a dot 1 is also a. We know that a plus a complement is 1. We also know that a dot a complement is 0. We know that a plus b is the same as b plus a. We also know that a dot b is the same as b dot a by the commutative law. It also means that a dot bracket b plus c, or if I don't even put a dot, just a outside, it means I can still distribute a over that addition. It also means that a plus a is a and also it also means that A dot A is A. So these are some of the things that you need to have for you to be able to play around manipulating De Morgan laws, your Boolean laws. Then we can look at quickly. We can look at the De Morgan, which says that if I have got A dot B complement, it means that I can distribute A complement plus B complement like that. It also means that if I've got A plus B complement, it also means that it's A complement dot B complement. These are handy laws that you memorize later on if you have not yet done so. So when you are told or you're given an expression where you are supposed now to simplify, then it becomes a magic to say, because some of these laws, like another important law, is to say that A plus 1 is 1. Now, it does not matter, because here we are dealing with on and off. We are dealing with binary numbers. So it does not matter the value of A. It still remains 1, because even if it is 1, it's still 1. Even if it is 0, it's still 1. So you need to play around with those other laws so that your life is easy. Now, suppose we are told to simplify. Suppose we are told to simplify A complement B complement C complement plus I'm trying to find an example where it will address all the issues that we want in once, so that we be able to really see what I want you to see in terms of grouping certain things, so that you'll be able to simplify those things. Let me see if I can be able to bring out a proper example for you to be able to appreciate how you simplify Boolean expressions in that instance. Then I want to put something like A, B, C like that, so that I play around with that. I play around with that. So let me try to group these nice things. Let me try to group these things so that you'll be able to appreciate the laws that I want you to have. Now, because when you are looking at these expressions and you're trying to simplify them, it's good that you identify things that can be found in terms of in common. Like if I look at the first term, because I know that from the laws that I have been given you, I know that let me see if, because I know that let me see if I've given you that law. I know that where is it? Right, this one. A plus A complement is equals to 1. So I can try to use that same fact to play around with that. Right. So if I'm here, if I'm using these terms, I can factor out this. I can factor out B complement C complement. If I factor out B complement C complement, I will have inside A complement plus A plus. Then it means I've dealt with the first two terms. Then I can move on to inspect the third term. And I want to make sure that now if I am at the third term, if I'm there, if I take this term and this term, I see that I can factor out A, B here, and I'll still have C plus C complement, which means I have dealt with that, I've dealt with that. I'm left with those two terms. Plus. I see that B complement C is common. I can factor out B complement C here. B complement C, then I have A complement plus A. So ordinarily I have got B complement C complement plus AB plus B complement C, where all these are ones, and they will be eliminated. Now, I see that the first and the third term, I can play around with them. I can play around with them here. I can factor out B complement. B complement. Then I'll still have got C complement plus C plus AB. Then I'll reduce this one to B complement plus AB. Later on, I can leave it there, but there is another complement absorption law. Obviously, it is only for the few that would have read that far, which will absorb B, but you can still leave it like that. But it's still correct if you leave it here, or you can go an extra mile to absorb B there by the complement absorption. So that's how basically you simplify those, you group them, then you simplify. You group them, then you simplify. I can still look at simplify A B complement plus B complement C, then A B complement plus complement C. The issue is to simplify. I can straight away get into it and have this one and this one. It will give me AB complement dot AB complement. This one plus AB complement C complement plus this one and this one. This one, it will give me A, B complement B complement C plus B complement C, C complement. Right, we'll move on. Now, this one is the same law, A dot A is equals to A. We looked at this. So I'm going to have A, B complement plus A, B complement, C complement plus is the same thing that we have been talking about A dot A. So it's A, B complement C plus, obviously this one goes to 0 because of the C complement dot C. So I can see that AB complement is common. I can see that. I can factor it out. AB complement 1 plus C complement plus C. Then, as I was telling you, this one will go to AB complement. Then I'll stop there now. Because whatever is in the brackets, as long as there is 1, whatever the answer there is to come to 1. And 1 times that AB complement will have AB complement. Right? People can go on and on and on and on, trying to simplify these nice things. Let me try to draw a bit of gets before I let you go. Before I let you go, I'm getting tired now. So AB complement. We said by the De Morgan law, it's A complement plus B complement. So AB complement from the it's an AND get whose output has got a 0 to mean it's negated. This get is equivalent to A and B, which are negated. If I want which are negated like that, then they are going into an OR get. They are going into an OR get. I can play around with the OR get like that. Then I have that. Then I have that. Play around with that. Play around with that. Now, you should be able to draw these gates. You should be able to draw them because you have got an AND gate, you have got an OR gate, you have got an exclusive OR, right? You should be able to just manipulate so that once you are given then you'll be able to quickly draw the gate. Then you should be fine after drawing the gate. I want to have a clean page where I can put a big gate just to answer one problem on gates. Then we should be okay in terms of how you calculate your gates. So we can have one example. We have one example that is covering all that. So I can have an expression. So you should be able to, once you are given an expression, you should be able to draw a logic gate, or once you are given a logic gate, you should be able to come up with an equivalent expression for that same gate. It's either way. Either you are provided by a gate, then you are told to give us an output, then you follow the output at each gate, else you are given an expression, then you're asked to come up with a logic gate. Let me try to just have one big one that will help you to be able to address all these problems once. So I'm having a complement, and my complement is ending, it's not covering D, it's just covering this A, B plus C, that's my complement. Then I'm going to have that one, it's a plus, that is the exclusive OR. Then I can have another one there where I will have CD, then plus B, then plus A, then I'll close like that. Then I will have, let me close here. I will have one complement on top that is complementing everything in terms of the output there. One complement on top that is complementing everything. So step by step. So I'm going to draw this part. I draw that part. I join it together using the exclusive OR. Let me start to draw A, and B complement, which means that it's an AND gate, but B is complemented. So I'm going to have A there, I'm going to have B there, then I'm going to complement B, then I'm going to have an AND gate like that. then plus C. Then I'm going to introduce a C from somewhere. Then I'm going to have the output of that getting into an OR gate. Because we have got a complement in terms of that's the one that I was saying is not covering D, so the output has got a complement, right? Then that one is being multiplied by D. I'll introduce a D. Then I'll put an AND gate to that effect. I'll put an AND gate to that effect. Then I await that outcome. I'm done with this first bracket. Then I go on to the other one, C, D, O complement, which means it's C and D, but the output is the one that is under complement. So I can still use a different, I do this for purposes of clarity. You can still put down a D, put down an A, but there's no harm also in just introducing another C and D, because these are just wires that you're working on. I'll try to, I hope from this end it should be visible. Let me try to just put it above that so that we have contact. So it's C. Okay. The output is under complement plus B. I'll introduce another B. Then they are being joined by the OR gate. Then plus A, the output is, I'll introduce another one, A. Then I'll join them again with an OR gate. Right? Then the output, now the output is being joined to everything by an exclusive OR, which is under an exclusive OR gate. Then because of the bigger complement that I was talking about, we complement the output. So that's how you come up with that. It should be nice. It should be easy for you to come up with that. So once you are given something like that, you can still go back and write outputs, join them, and still come back to the same place where we started. Or if you are given that one, you can still have the output. If you are given an expression, you can draw a gate without any hesitation or problem, provided you know those gates and provided you know the meaning of those nice things. Right. I think that should be it on my on Boolean algebra. We are jumping a lot of other things, so that one thing that I want to do with people here is a 3x3 simultaneous equation. People can at their own pace do calculate the inverse of a 3x3 matrix. But let me try to work myself. I just want to do one 3x3 simultaneous equation. Then I think I would have covered most of the things. In fact, I would have just left a 3x3 matrix. Teach it out at least to that's how we hope. That's how we will find the serious ones and those that are not serious. So I want to have one 3x3 simultaneous equation. I'm going to adopt the method of the generic method that people are used to. You can do your substitution, you can do elimination. If you are not told what method to use, then you can still go on and work out the way you want it. There are different methods. You can use the Gauss-Jordan, you can use the Gauss elimination, you can use the different methods. But the idea is whatever method should lead you to a correct answer. Right? I'm going to pick a simple one for purposes of demonstration. X plus 2y minus z is equals to minus 4 minus 2x plus 4y minus z is equal to 6. Then the last one, 2x plus 2y plus 3z is equal to 1. So on your matrices, that's where we are having this section on simultaneous equations, which is yet another section that is going to come in the exam. So your simultaneous equation, you will know whether you've gotten it right or wrong. You will know, because when you test it back into the original question, when you put your x, your y, and z, if they're not going to where the answer is, you will know this one I did not get it right. So don't even expect that someone is going to be merciful in terms of conspiracies, etc., etc. Maths, a lot of other theory that people write what they want, then just they say nambonyora anozongoona zvekuita. Maths dzakasiyana nezvozvo. If the method is wrong, if the answer is wrong, then it is 0. Right. Let's try. So I can number my equations if I want to 1, 2, and 3. But by inspection, I can see that if I'm going to number my equations 1, 2, 3, I can add 2 and 3 because I'm making use of that minus 2x and that 2x. Once I add them, I eliminate x. Then I can work with x, with y and z. Then I try to pick number 1 and one of the equations again. I eliminate x again, so that I've got 2 equations in y and in z. I solve for y, I solve for z. Then I can substitute back y and z, then find x, then test my things, then I'm good to go. Right, so I'm going to number 1, I'm going to number it 2, I'm going to number it 3. So by inspection, I can see that if I say plus 2 and 3, for example, I'm going to have 6y plus 2z is equal to 7. I'll call it number 4. Now, if you don't number your things, you are going to land yourself into a big trouble, right? Now, I can choose number 1. I have not used number 1, but I can choose any one of these. I'll choose 2 because I want to quickly eliminate x. What I'll do is I'll say equation number 1 so that I raise the coefficient of x to 2 there. Equation number 1 times 2. I will have what? I will have 2x plus 4y minus 2z is equals to minus 8. I'll call this equation number 5. So ordinarily, what I want is to say equation number 2 plus equation number 5. Right, so this one and that one, it goes, that one it will give me 8y, then that one and that one, it should give me minus 3z, that one and that one, it should give me minus 2. I should call that equation number 6. Let me see if I did not make any errors there. So I think it's okay. I think it's okay. Now, I have got equation number 4 and I've got equation number 6. They've got both terms in y and z. Now, I want to eliminate z, then I find the value of y. I substitute back the value of y into either 4 or 6. I get z, then finally I can find x. Now, to eliminate z, I see there's a minus 3z there, and there's a positive 2z. So by inspection, if I raise both of them to 6, the coefficient of z, if I raise them to 6, if I add them together, I'll be able to eliminate z. So what I'm going to do is, I'm going to say equation number 4. I'm going to multiply it by 3. So that I have got 18y is plus 6z is equals to 21, which is equation number 7. Then equation number 6 times 2, so that I make use of that. I will have a 16y minus 6z is equals to minus 4. I'll call this equation number 8. Then I add equation number 7 plus 8, so that I got 34y, right, is equals to, this is a positive 17. So I can have y being equal to 1/2. I move on. I want to substitute y in 6 above. I'm just picking 6. I can either pick 6 or 4, or let me pick 4, right? 6y, that's 4, plus 2z is equals to 7, right? So it's 6 half plus 2z is equals to 7. So I've got 3 plus 2z is equals to 7. I take 3 the other side, 2z is equals to 4, then z is equals to 2. So I have got z, I've got y, then I can substitute in either 1, 2, or 3 above. I'll pick 1. X plus 2y, x plus 2y minus z minus is equal to -4. Minus z is equal to -4. Let me now. So my things are okay now. X plus 2 bracket 1/2 minus bracket 2 is equals to -4. Then I can have x plus 1 minus 2 is equals to -4. So I know that it's now x minus 1 is equals to -4. I can take that other side, so that I finally have my x is -3. So I can test now either with 2 or 3, so that I have got my lovely things coming out as nice as I want. It has been a pleasure having you. You are going to work on matrices, going to work on 3x3 matrices, the adjoint, the matrix of cofactors, the determinant, and if you have got also, you can also even look at what we call the identity matrices, etc., etc. But that should be it in terms of what you need to work on. And I think I've touched almost everything that I wanted you to have. So you can go ahead, go and enjoy yourself. And I wish you the best in the exam, so that I'll continue to say this. When people are told that this course has made some to drop the whole program, they think, I don't pay a road. It's not basa. Then people, they don't read. But I'll tell you one thing. But it's the truth. So I will still say what I said here, that it has got the highest fail rate. We hardly pass 50% in terms of passing. Right. I have got 58 students registered in Bith. I've got 158 students registered in Bsit. We will not have people 50% passing. Why? Because people, they decide with one order and wapinda next. you become a casualty. So make sure you revise. Make sure you work them out. Make sure you are thorough. Make sure you know what you're doing. Make sure you revise everything. Section by section, section by section. Right? Make sure you know. I know that people, what they do is when assignments, due dates are coming, they just shower an item, change the cover page. Yes, we don't want to but kana ukasazoteerera zvinhu zvachona zvaunga uchingokopesewa neumwe imhaka dzako. Asi hatina zvimwe zvekucharamba tichitaura besides to say vakamboonana havashayane, all the best in your coming exams. I think I'm done here. I'm leaving the meeting unless there are pressing issues that you want me to address. You see hazvo zvemamarks nechi zvimwewo zviri pressing. Right, I think things are in order. Then I'm leaving the meeting. Then you can continue to enjoy yourselves after that.
Thank you, sir.
Right, ndina recording.
Thank you, sir.
Aprimei chakurekodha zvikanzi tikurekodha, saka musazotininga muchiti tatina kuwana, hatina kudii, hatina recording yandaita ini. Saka mupedzerana nemabhori renyu angoiwo.
Tapedza man.
Someone's wasting it.